Ramtin, go.
Okay. John sang Lee, Jarek, I'm sorry if I pronounced your name wrong. Tobias Kim, Arthur, Thomas, Victor, Hayden with H, Sudarshan, Hank, Ethan, Matthew, Nick, Andrew, Maya, Ryan, and Julie. You guys have not paid your deposits.
Oh.
You should do that as soon as possible.
UCLA IEEE. Sorry, UCLA IEEE Venmo.
What was that?
I paid someone.
Your name?
Did you put your name in the project?
Maya.
I did put my name in the deposit, yeah. It's good.
Okay.
We'll check with this treasurer. Yeah, do you have a? Okay, I'll double check with Taylor.
University of Colorado.
University of Colorado.
Yeah.
That would be if we were teaching power electronics, but we're not.
We don't have that here, so.
There's a power electronics class.
Once every 2 years.
Yeah, if any of you guys is interested in power electronics, that's the place to go.
Yeah, it's a terrible.
Huh? It's yours? No. What is that? Who drinks that?
I don't know, an animal. Something.
I think it's because my
Thanks, Steve.
Oh.
Okay, so
I drink this too.
Oh, yeah.
You're experiencing a significant decrease in the number of people present, but that's okay and expected. So today's lecture is going to be about oscillators. Let's go back to the days of trigonometry, where we first learned what a sine is. T graphs phi, and somebody told us that this is by sine of t. Okay, and we learned a bunch of mathematical techniques to manipulate this sign, trig identities, and all of that. But what nobody told you was how to even generate this sign in the first place. How do you do that? Does anyone know? Well, that's the whole purpose of this lecture, to figure out how to generate something like this, because it's going to be useful for our circuits, and you will see why it's going to be useful in the next lecture, actually, when we go over mixers. So for now, our goal is to generate a sine or a cosine wave that has a very specific frequency. One way that is probably familiar to you is using an inductor, a capacitor, and a resistor. So what's going to happen is that the magnetic energy inside the inductor is going to be transferred to the capacitor, and then from the capacitor's electric field, it's going to go get stored in inductor's magnetic field. However, there's always some resistance in the circuit which acts as a damping parameter. So if we actually draw, let's say we are measuring the voltage across this capacitor. If we draw V capacitor as a function of time, what's going to happen is that we start at a certain charge, which gives us a certain voltage, and then it's going to go down, and then slowly with time, it's going to have an exponential decay. I have added some details in the notes. Feel free to go over them, but they are probably not as relevant as what we're going to discuss today. So the general formula for this wave is going to be V naught omega naught or omega d e to negative alpha t cosine of omega d t plus phi. And then each one of these phi, omega d, alpha, they all can be written in terms of L, C, and omega naught, R, and L, known quantities. So feel free to look at those in the lecture just for your own information. But yeah, the whole point of this is that this is going to decay, and we don't like that. And the reason for that decay is having a resistor there. So how can we solve this issue? Any ideas? we can get rid of that resistance. So, if this is, let's say, some value, 20 ohms, you agree that if I put a negative 20 ohm here, this will cancel this resistance? So negative R, done, problem solved. But the question is, how do you actually generate that negative resistance? So the way we do that is that we'll have our L, C, and resistance. And then we are gonna connect it to some sort of circuit, some sort of active circuit. And this circuit, looking into this port, is gonna actually have a negative impedance. So that for the whole circuit, that negative impedance is gonna cancel our R, and as a result, our LC tank will oscillate. So one way to actually generate that negative resistance is using this configuration called Colpitts Oscillator. So the way Colpitts Oscillator works is that you have your inductor. With any inductor, there is some series resistance, which is again that damping factor. And then we have our capacitor, but this time I'm gonna actually split my capacitor into two capacitors. So far this is the same old LC tank. And then I'm gonna connect another circuitry to this. Okay, so before we get into any sort of math, let's see why this even makes sense. So what's gonna happen is that as the time goes on, the charges that are getting stored on these capacitors are gonna go down. And this amplifier, which we discussed in the last session, is basically going to charge C2 constantly. So it will make sure that the charge will not go down in this LC tank. Now, if and this is the ground, if I cut this circuit from here, what do I have? I will have my L, my RS, and then it's getting connected to some block. And my job is to figure out what's the input impedance looking into this block. Okay, so far so good. So how do we do that? First of all, oscillations are considered AC signals, for which we use small signal model. So let's draw the small signal model of this part. So this is going to be the base, my emitter, and my collector. So between the base and the emitter, I have my RE, no sorry, between the emitter and the ground, I have RE, and I also have C2. Is it C2 or C1? Why is it C1? Okay. I have C1 here, C2, V pi. And then between the collector and emitter, we said we will have a current source. You remember? So this is our current source, which is generating GM V pi. And of course, between the base and emitter, we have our C2, which is this here. Now, in order to measure the impedance of this circuit, the typical way to do it is that we connect a voltage source, which generates our AC signal. So let's call this Vx, and then we see how this current changes. And then we divide voltage by the currents, we get our impedance. So far, so good? Any questions? So I've included the calculations for Vx over Ix in the notes. Feel free to go over them. You should actually go over them because we are thinking about putting a problem in the assignments so that, but it's going to be a different oscillator. You guys have to use the same technique to find the impedance of that oscillator and do whatever we're going to do after this. So if we do a bunch of KVL, KCL, what we will get is that Vx over Ix is going to be equal to, which we are naming it Zn for now, minus Gm C1 C2 omega squared plus 1 over J omega C1 plus 1 over J omega C2. This is the impedance looking into here. So what's good about this? Can anyone tell? What is this impedance telling us that is very desirable? The negative, exactly. The real part of this impedance here is a negative value. And we also get an imaginary part, which is also desirable because we have an L. We would like to have a capacitive. We would like to have a capacitive behavior in this circuit as well, so that we have our L and C combination. And then this is our negative resistance. So, if I want to fill this out, what I'm seeing is one cap and one resistor. And the value of my resistor is negative Gm over C1, C2 omega squared. And can anyone tell me what this capacitor is going to be equal to?
Going to be the 1 over J negative C, right?
That's going to be the impedance of that, that's right. So the impedance of this capacitor is going to be 1 over J omega times 1 over C1 plus 1 over C2, which is 1 over J omega times C1 plus C2, and then over C1, C2. So if I were to set that equal to J omega C effective, my C effective is going to be C1, C2, C1 plus C2, which is nice because this is exactly the expression that you will get for two capacitors in series, right? And there it is, exactly the circuits that we were looking for. We have our inductor, capacitor, resistance, and negative resistance. So any questions so far about this? Does it make sense? Not too complicated, is it? Okay. So what relation should I have between my negative resistance and positive resistance? Should it be, like, what can I say about the absolute value of those? Yes, Kaden.
Ideally, like, if we're not saying if there's anything else, then we want them to be the same, but just opposite.
Yeah, they should be the same. What else? Can the negative resistance be higher than the positive one?
If you have the negative resistance be higher, then you'd be like continuously adding energy.
Yeah, but at some point it's gonna stabilize, like any other system. So technically speaking, as long as, even if I have a negative overall resistance, this will still oscillate. And actually what we will do is that we want this negative resistance to be by the order of 5 or 10 times larger than this RS. And the reason for that is the GM value changes with temperature. So we want to make sure that if our temperature changes, this negative resistance is still more negative than if we were to negate this RS. So the rule that we will follow is that negative GM over C1, C2, omega naught squared has to be larger than or equal to RS. Or in other words, GM has to be larger than or equal to omega naught squared C1, C2, RS. The interesting thing about this is that if RS was 0, my GM could also be 0, meaning that I didn't even need that transistor circuitry. I could have just connected my L to these two capacitors and it would oscillate, which is what we expect because we don't have RS. So this is the golden rule of Colpitts Oscillator. And one more thing to mention is what's happening at the resonant frequency. Can anyone tell me what the resonant frequency is for an LC tank?
Just 1 over root LC.
Yes, that's right. Basically, it's a frequency at which the impedance of our L is the same as the impedance of our capacitor. So meaning that if I were to add them, I shouldn't see any resistance, any impedance in my loop. So the impedance here is going to be J times L omega naught. The impedance here is going to be 1 over J C1 omega naught, and then the impedance from the next capacitor is going to be 1 over J C2 omega naught. And we want this to be overall 0, which means L omega naught is equal to 1 over C1 omega naught plus 1 over C2 omega naught. And just doing a bunch of algebra. L omega naught is equal to 1 over omega naught C effective. So omega naught, as Caden said, is going to be equal to 1 over square root of L C effective. And we said that C effective is C1, C2, C1 plus C2. And that's the second relationship. All right, any questions?
So,
We're good?
I wanted to add on to Caden's question a little bit. So, Caden, you're right in that if you have a negative GM over that expression that's much greater than, your RS, you're gonna be adding voltage and it's gonna, become unstable. Okay? But the thing is, we're taking our signal and we're feeding it into our transistor. And because we're feeding into our transistor, we're gonna get to a certain point where the transistor can no longer amplify anymore. And that's what's called saturation. And so actually when you hit saturation, it's gonna do this effect called clipping. And clipping will actually distort your signal a little bit. What turns your sine waves into like,
Like flat on top.
yeah, this to, yeah. Thing is, in practice, it doesn't distort it that much. So like, you're chilling. Yeah, that's not that bad. But you're right, it would be unstable if it were not for the transistor. So what Ramtin talked about was one way you can analyze and design this. I'm going to talk about an alternative way. Same idea, but we're going to show a different method of analysis and arrive at the same results.
Yes, and you should understand both methods.
Yes.
Please. They're useful.
I'd say this one's a tad easier. But
As
I
is
think,
math,
I
for
think
sure.
Ramtin's is more generalizable and applicable to what you learn and have to do in industry.
Yeah, so when we get to the hardware phase, if you happen to be in the team that's designing the oscillator, you can use this technique to basically analyze any oscillator that you will see and calculate what sort of transistor circuitry you need for it.
Yeah. So this method, we're going to look at it in a systems perspective. So we're going to as connecting two modules. Here's going to be your oscillator. And then of course here is your amplifier. This is a common collector amplifier, but still an amplifier. Okay, and so we can model this at a higher level through a feedback loop, looking at, say, this node over here and this node over here. Okay, so this is a node we'll call VF, and this is V out as it's connected to V out. So that ends up looking like so in this block diagram, AV is going to be the gain of your amplifier, and beta is going to be the gain or attenuation of your oscillator. And so at a high level, we want to somewhat balance the gains such that we're producing a consistent V out. So what you can do is you can look at this thing over here. We already know the gain of a common collector amplifier. It will be the impedance at the emitter over 1/GM times plus the impedance of the emitter. Okay? So knowing this, we need to solve for the oscillator, the gain of the oscillator. And to do this, we can model the oscillator, of course, as a transfer function. I can do the derivation after if you want, but actually I'll include it in the lecture notes. It's not currently in it, but we'll include it. But basically, the gain of this will also be this. Beta equals VF over V naught equals JXL. So I don't know if you guys are familiar with this kind of notation, but X will be impedance, so XL will be the impedance of your inductor, and X1 will be the impedance of your capacitor. And reactance, yeah. So for capacitor, which is J over 1 over J omega C, X is equal to 1 over C, omega C. And that's how you get negative JX1 for being the reactance of the capacitor or impedance. Okay, so we want to somewhat simplify this a bit. And the first thing to note is that when we look at this transfer function, usually your impedance of your inductor and your capacitor is much larger than your series resistance. So we're going to say that approaches 0. And what you're left with is this. And in resonance, the target frequency when we're operating at omega naught equals 1 over root LC, the reactance of the inductor equals the reactance of the capacitor. And in this case, as we see over here, this would be X1 and X2. So basically, the reactance of your inductor equals the reactance of your two capacitors added together. And so we can say our gain is now equal to your two reactances of your capacitors added together over when JXL equals X1 plus 2 minus X1, that's just your second capacitor reactance. And so split beta is approximately equal to X1 plus X2 over X2. This is, I don't know if this is right. This is equal to, it's actually right, C1 plus C2 over C1. You can show that. Okay, so now we know the gain of our oscillator, and we know the gain of our amplifier. And so for this system to work, we know the gain, overall gain has to be greater than 1, because if it's equal to 1, then when we start the system, we have an input of 0, and it's not going to go anywhere. So if we have an input of 1, then it's going to have an unstable reaction and plateau at the when the transistor has its cutoff, has its saturation, and will operate like that. This is actually a really cool example also of a good use of unstable circuits, by the way. Similar to like your D flip-flop, but anyways. Okay. So we know the gain of the amplifier, and that is the impedance at the emitter, okay? But it turns out the impedance at the emitter is not so simple. You have this resistor at the emitter, but also this whole unit. Yeah, and so if you were to model the impedance at the emitter, it'd be ZE equals that resistance at the emitter in parallel with C1, so that C1 goes to ground, or Z1 we'll call it, in parallel with, you know what, I'll just draw this. Okay. Yeah.
Oh, I think for the second explanation, you can flip C1 and C2 because
This thing?
So basically,
I think this is right.
That's right.
Yeah.
Just on the picture, because
Oh.
like when I was deriving it, I changed them.
Sure.
So yeah, C1 and C2.
All right. Let's actually look at ZE, if we're looking into here, what would ZE be? And if we were to redraw it, it would be, we have RE, C2, C1, RS, and then this would actually be the input impedance of your amplifier. Z amplifier. Okay, and then we know that the input impedance of your amplifier is going to be very high because we're using very high biasing resistors. So we'll assume that's basically an open circuit. You can also assume that compared to your capacitance and your series resistance plus your inductance, that your emitter resistor is also very high because your emitter resistor is on the order of 1,000 versus your capacitance and your inductance will not be on that order.
Yeah, like 1 over J omega times C2 would be much smaller than
Yeah.
kiloohms.
So really your ZE is approximately C2 in parallel with C1 plus L plus RS. Which is, if you were to write it in terms of reactances, it would be equal to JXL, which is your inductor, plus RS, plus or minus JC1 times JX2, sorry, X1, X2, over JXL minus JX1 minus JX2 plus RS. And let's see. So you know that at resonance, again, your capacitance added together should equal your inductance. So this cancels out. And what you're left with is, oh, and this thing over here, these two, that can simplify to JX2. So JX2 plus RS times negative JX2 over RS equals X2 squared plus RS X2 over RS. And again, your series resistance comparison is going to be small. So in this term, so that goes away. That's approximately X2 squared over RS. So given this, we can plug this, you can plug ZE back into our gain of our amplifier, which is X2 squared over RS. So AV equals X2 squared over RS over X2 squared over RS plus 1 over GM. And let's see. And eventually we're going to do, we want AV times beta to be greater than or equal to 1. And if you plug in everything, you'll rederive what Ramtin wrote out originally, which was GM is greater than or equal to omega naught C1, C2, RS. So basically, through two ways of approach, we can get the same kind of relation. Yeah.
questions about either one of the approaches that we discussed? Yeah, so we talked about the Colpitts oscillator both in terms of circuits and impedances and at control system level. This that we discussed, AV times beta has to be greater than or equal to 1. It's called the Barkhausen criterion. If you guys are interested, you can always Google that and see what's happening. Basically, Barkhausen is used to make sure that our amplifications and our feedback loops are stable. Whereas here, we actually don't want it to be stable. We want it to be oscillating. So that's why we are doing kind of the opposite of it.
Yeah. Usually it's, yeah.
Yeah, if you take 115B, you will cover this. And 141. Okay, yeah. I haven't taken 141, but yeah, Toby has taken it. So.
Just, I don't know, but
I mean, you look at it more in the S plane, right?
yeah, basically.
Yeah. So in the S plane, no, this isn't as easy to translate. Yeah, because the meganauts on the y-axis, but whatever.
Yeah.
Yeah. Or I guess in the S plane it'd be like this. Here's the meganaut that you're looking at. You want to go this range up here, like that. I think it's how I look in the S plane. But
Alright, sounds good.
Yeah.
Just a heads up for the next lecture, please review amplitude modulation on your own. It was one of the questions that we asked in the application to explain what it does in the frequency domain, and it will come up in the next lecture when we talk about mixers. So make sure you review anything that you need to review so that you will understand what's going on with the mixers. And this oscillator will show up in the next lecture as well.
yeah, and so also for assignments, assignment 1's due on Thursday. Make sure you have that done. Assignment 1 includes your lab safety training, your deposit, and the entire assignment. An assignment can take a while. It took some people like 4 hours with us being there.
Yeah.
So I'd recommend getting started on it. This will probably be one of your more lengthy assignments until we get to actual design stuff. Then you'll be spending a lot more time. Yeah. Yeah. And we'll drop assignment 2 on Thursday. Yeah.
Okay, then that's a wrap.
Yeah. Thank you.